Welcome to lecture 46. This is the first lecture of week 10. In this week 10, we will talk about constrained nonlinear programming. As of now, we have talked about optimality conditions for single variable unconstant problem, multivariable unconstant problem, constraint problems. We have seen how to solve unconstrained single variable and multivariable problems. We have also seen how to solve linear programming problems. In this week, we will see how to solve a general constrained nonlinear programming problem. So, there are various methods of solving a constrained nonlinear programming problem. Some of the methods that we will talk about are sequential linear programming method, successive quadratic programming method, penalty function method and Lagrange multiplier method. So, today we will learn about sequential linear programming method, and as the name suggests, a nonlinear programming problem will be solved by a series of solving linear programming problems. So, before we start solving constrained nonlinear programming problem, let us first review the KKT conditions or Karush-Kuntakar conditions for a general nonlinear programming problem. What you see is the statement of a general nonlinear programming problem: minimize f x where x is n vector, subject to p inequality constant, and let us say you have m equality constants. Idea is you have a general nonlinear programming problem where you have decision variable, n number of decision variables and several inequality and equality constants. So, first we formulate the Lagrangian. So, to formulate the Lagrangian, we multiply the equality and the inequality constants with their corresponding multipliers and add them up with the objective function. So, once you have the Lagrangian, the first KKT condition you write that the gradient of the Lagrangian will be equal to 0. Second, feasibility check, that means the inequality constant has to be satisfied, equality constant has to be satisfied. So, the candidate solution or candidate optimal solution will satisfy the inequality constant as well as equality constants. X star is the candidate optimal solution. We let us see that we will call this a KKT point. The point that satisfies all the KKT conditions are known as KKT points. Third KKT condition is switching condition, which says that the product of multiplier of the inequality constants and the inequality constant will be equal to 0. The non-negativity of Lagrange multipliers for inequality constants, and finally, the regularity check, which says the gradients of active constants must be linearly independent. So, these are the KKT conditions for a general nonlinear programming problem. The points that satisfy all these KKT conditions are known as KKT point. So, a KKT point is the likely candidate for optimum. Remember, the KKT conditions are first order conditions for optimality. So, the KKT conditions are satisfied by the KKT point, and the KKT points are likely candidate for optimum. To further check if the KKT point is true optimal or not, we must make use of second order conditions, and you have seen those things in our previous lectures. Now, what you see is a pictorial presentation of a linear objective function and nonlinear constants. And let us say this is the optimal solution. Here what you see is the constants are all linear. So, the feasible region is constructed by the linear constants and the objective function is nonlinear, and let us say this is the optimal solution. Look at the difference between the linear programming problem and the nonlinear programming problem. Here the objective function is linear, but the constants are nonlinear, and here the constants are linear, but the objective function is nonlinear. But a general nonlinear programming problem will have both constants and the objective function nonlinear. So, you can have a situation like this, where you have nonlinear objective function and nonlinear constants, and the optimal solution is this, let us say. But this is not necessary that the optimal solution will always lie there, as here we have a nonlinear objective function and linear constants, and maybe the optimal solution is lying well within the feasible region. Note that for linear programming problem, the optimal solution will always be a corner point. So, optimal solution could have been here, 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 in any of these corner points, or maybe here. But in case of nonlinear programming problem, the optimal solution may lie anywhere within the feasible region. Now, let us talk about the techniques or methods that are available for solution of constant nonlinear programming problems. The methods available for the solution of a constant nonlinear programming problem can be classified into two broad categories: direct methods and indirect methods. Direct methods handle the constants in an explicit manner. Generally, indirect methods solve the constant problem as a sequence of unconstrained problems. Some examples of direct methods are random search methods, heuristic search methods, sequential linear programming methods, sequential quadratic programming method or successive quadratic programming method, generalized reduced gradient method. Some of the indirect methods are transformation of variable techniques, sequential unconstant minimization, penalty function method, augmented Lagrange multiplier method. So, we will briefly talk about some of these methods in this week. Let us look at some characteristics of a constant optimization problem. It may happen that the constant has no effect on the optimal solution. In other words, the unconstant optimum and the constant optimum are the same. This is what you see on the diagram. Note that the feasible region is such that the constant optimum is same as unconstrained optimum. In this case, the minimum point x star can be found out by using the necessary and sufficient conditions for unconstant minimization, that is gradient at x star equal to 0 and the Hessian at x star is positive definite. So, that x star is a minimum point. But the constants, when they are present, will usually have a different optimum than the unconstant case. Look at the diagram shown. Let us say we are solving a maximization problem. So, this point is the maximum point. You can see from the contours that as we approach this point, the function value increases from 50 to 55 to 56, so on and so forth. So, now if this is my feasible region, my constraint maximum will be this point. Because note that this contour represents a higher function value than this contour. So, constant optimal will usually be different, but not necessarily so. Optimum may occur at constant boundary, and we have seen when we talked about necessary conditions in our previous weeks, that according to KKT conditions, the negative of the gradient can be expressed as a positive linear combination of the gradients of the active constants. So, this is what happens when optimum occurs at constant boundary. Look at the diagram. The active constants are G1 and G2. G3 is inactive. Point x is optimal So, the negative of the gradient of the objective function can be expressed as a positive linear combination of the gradients of the active constraints G 1 and G 2. A constraint optimum problem, a constraint optimization problem can have multiple optimal solutions. If the objective function has multiple unconstant local minima, the constant problem may also have multiple minima. Sometimes even if the objective function has a single unconstant minimum, the constraints may introduce additional local minima. That means, your unconstrained objective function may have a single minimum, but the constrained objective function may have multiple minima. So, now let us see how we can solve a general nonlinear programming problem using successive or sequential linear programming method. So, what are the basic steps? The original nonlinear programming problem is solved by solving a series of linear programming problems. Each linear programming problem is obtained by approximating the nonlinear objective and constant functions using first order Taylor series expansion about the current estimate of the optimum. That means, about the current estimate of the decision variable or design variable vector. The linear programming problem can be solved by say simplex method to find the new decision variable vector. If the new estimate of the solution is not the desired or converged solution, the problem is relinearized about the point about the new estimate, and the procedure is repeated until we find the optimal solution x star. So, the method is as follows. We will solve the nonlinear programming problem by solving a series of linear programming problem. So, first thing that we ask is how do I get this linear programming problem from a general nonlinear programming problem. So, what we do is each linear programming problem is obtained by approximating the nonlinear objective function and the nonlinear constant functions using first order Taylor series expansion, and we perform the first order Taylor series expansion around the current estimate of the optimum. Let us say the current estimate is x I. So, perform Taylor series expansion of the objective function as well as constant functions around x I. So, then you will have a linear programming problem. This linear programming problem can be solved by simplex method, and you will get a solution which is an improved estimate of the original nonlinear programming problem. Let us say that estimate is x I plus 1. Now, if this x I plus 1 is the desired solution or the converged solution, we stop. If not, we relinearize, that means we linearize the nonlinear programming problem again around this new estimate x I plus 1 and repeat the procedure. So, we continue to do this until we converge to the optimal solution or we are very close to the optimal solution. So, now let us first take the case of linearly constant nonlinear programming problem. So, first we consider the case where the nonlinear programming problem have only linearly constrained functions as constants. So, constants are all linear. So, you can write it as minimize f x subject to a x less or equal to b, and we also have non-negativity restrictions on x. Note that this differs from standard linear programming problem only in the presence of nonlinear objective function f x. So, if the objective function f x is linear, this will be same as the linear programming problem that we have seen in previous lectures. But a linearly constrained nonlinear programming problem differs from standard linear programming problem only in the presence of nonlinear objective function. So, now the optimal solution can lie anywhere within the feasible region, not necessarily on the corner points only. For a linear programming problem, the optimal solution will always lie on the corner points, but for a nonlinear programming problem, the optimal solution can lie anywhere within the feasible region, including the corner points. The linearization of the linearly constrained nonlinear programming problem around some feasible point x 0 is clearly a linear programming problem, and it will have an optimal solution at a feasible corner point, provided the feasible region is bounded. So, this I have as linearly constant nonlinear programming problem. So, I linearize this problem around some feasible point x 0, and we obtain this linear programming problem, because now I have objective function linear and the constant was already linear. So, this linear programming problem has a solution on any corner point. Of course, we are assuming that the feasible region is bounded. But how this solution of the approximate problem, that means the linearized problem, is related to the solution of the original problem? The solution of the approximate problem or the linearized problem will always lie on the corner points, but the solution of the original problem may lie anywhere within the feasible region. So, some type of line search is required in order to approach the solution of the original problem from the approximate solution. So, we have this algorithm called Frank-Wolfe algorithm, which can solve the linearly constant nonlinear programming problem using sequential or successive linear programming. So, in the step 1, we define the starting point, and then we define two termination parameters epsilon and delta, which are small positive numbers. The current estimate is used to find out the gradient. So, find out the gradient at the current estimate. If this value is very small, we stop. Otherwise, you go to the step number 2. In the step number 2, you solve a linear programming sub problem, which is defined as shown. So, let y be the solution, optimal solution to the LPP, y t. So, then we do some line search, find alpha, which minimizes f of x t plus alpha into y minus x. where alpha a number between 0 to 1. So, then we get the estimate of next x t, which is x t plus 1 as x t plus 1 equal to x t plus alpha t into y t minus x t. If the difference between x t plus 1 and x t is very small, or the function value at x t plus 1 minus x t can be written as less than epsilon into function value x t plus 1 mod of that, we will stop. So, we will check this convergences using both the termination parameters. So, if the convergence check is satisfied, we stop, otherwise we again go to step 1. So, now let us look at the case of general nonlinear programming problem, how a general nonlinear programming problem can be solved by sequential linear programming method. So, let us consider a general NLP as shown, minimize f x subject to g j x greater or equal to 0, j equal to 1 to j, h k x equal to 0, k equal to 1 to k, and x is bounded between lower bound and upper bound. Solution to this linear programming problem. Okay. So, given an estimate x t, we can linearize this given nonlinear programming problem by Taylor series expansion. We retain only the first order terms and can get this set of expressions or this linearized problem. Note that f x has been linearized around x t as f of x t plus gradient of f evaluated x t into x minus x t. Similarly, the inequality constant has been approximated using Taylor series expansion. Also, the equality constant has been approximated by performing Taylor series expansion and retaining first order term. So, solution to this linearized problem or linear programming problem gives us x t plus 1 as solution. If x t plus 1 is infeasible, we will re-linearize the original problem at x t plus 1, and this will continue until we converge. So, let us take an example, minimize f x equal to x 1 square plus x 2 square subject to x 1 square minus x 2 greater or equal to 0, 2 minus x 1 minus x 2 square equal to 0, and x 1 has upper bound as 2.5 and lower bound as 0.5. Similarly, x 2 is constant between 0 and 3. So, we want to construct the linear approximation to this problem at x 0 equal to 2 1. So, 2 1 is the current estimate. So, let us find out the gradient of the objective function. We found it out as 2 x 1 and 2 x 2. Evaluate it at 0.21. So, you get 4, 2. The function value at point 2 1 is 5. So, now the objective function is approximated by performing Taylor series expansion, and we get this. So, this is f of x t, this is the gradient, and this is x minus x t vector. So, now let us do the same for the inequality constant, and you get this as the linearized inequality constant, and also let us do the same thing for equality constant, and we get this as the linearized equality constant. So, when you put all these things together, we get this linearized problem for the original nonlinear programming problem. This linearized problem or the linear programming problem has a solution 11 by 9 as x 1 and 8 by 9 as x 2. Let us check if the inequality constant and the equality constant are satisfied. Inequality constant is satisfied, but equality constant is not satisfied, is minus 0.0123. If it is very, very small, we will take it as 0, but we can do better. So, therefore, we will reinitialize the problem, that means we will relinearize the problem at x 1, which is 11 9 and 8 by 9, and we will proceed as follows. So, basically what we will do is we will make use of this, this and this, but the points now will be x 1, that is that 11 by 9 and 8 by 9. So, that will give you x 2. We will continue to do this until we are very close to the true optimal solution, and the optimal solution, true optimal solution is 1 1. If you look at here, we are not very far from 1 1. It is a rough approximation of 1 1, but if we take 2 3 iterations more, just repeating the same steps, you will see that we are getting very close to the true optimal point 1 1. So, this is how we can solve a general nonlinear programming problem using successive linear programming methods. So, with this we stop lecture 46 here.